In this lesson, we're going to introduce transition metal organometallics, focusing on the preparation and reactions of organocuprates. Transition metal organometallics are typically made from the reaction of other organometallic reagents via a reaction called transmetallation. Transmetallation is simply the exchange of one metal for another metal within a carbon-metal bond. This typically involves the treatment of an organometallic reagent with a transition metal salt. The reaction is reversible. The reverse of a transmetallation is simply a different transmetallation. Product will only be favored when the newly introduced metal is more electronegative than the metal already bonded to carbon. The more electronegative metal results in a closer match to the electronegativity of carbon. This places less electron density on the carbon, resulting in the formation of a more stable compound. So here we see two examples. In the first example, a Grignard reagent is treated with cadmium chloride. We can see that the Pauling electronegativity number of the newly introduced cadmium is higher than the value of the magnesium atom bonded to carbon. Because the newly introduced metal is more electronegative than the metal already bonded to carbon, we can predict that this reaction will favor products. In the second example, we see an organozinc reagent reacting with magnesium bromide. The Pauling electronegativity number of the newly introduced magnesium is lower than that of the zinc already bonded to carbon. Because the newly introduced metal is less electronegative than the metal already bonded to carbon, we can predict that this reaction won't work and will greatly favor reactants. Studying transition metal organometallics could quite literally take an entire lifetime. We're going to focus on one specific type of transition metal organometallic, specifically organocuprates, or Gilman reagents. As you would expect from the name, organocuprates have a carbon-copper bond. Here we see a typical dialkyl cuprate, or Gilman reagent. Simple Gilman reagents will have two alkyl groups bonded directly to the copper atom. The copper is also bonded to an alkali metal, typically lithium. And don't let that second metal throw you off. The lithium is not bonded to the carbons in the molecule. As with most transition metal organometallics, Gilman reagents are produced via transmetallation. Here we see a typical example, in which two equivalents of an alkyl lithium are treated with one equivalent of a copper 1 salt. In this case, lithium bromide is formed as a byproduct. Just like organolithium and Grignard reagents, Gilman reagents can act as carbon nucleophiles. Gilman reagents can be used to form carbon-carbon bonds via a coupling reaction with alkyl halides. As you can see in this first example, one of the two alkyl groups attached to copper displaces the halogen of the alkyl halide, forming a new carbon-carbon bond. If you remember the alkylation reactions of classical organometallic reagents, this result might be rather underwhelming. This exact same transformation could have been accomplished with an organolithium reagent, specifically methyllithium. Remember that the alkylation of an alkyl halide with an organolithium occurs via an SN2 mechanism, and that SN2 reactions can only occur on sp3 hybridized carbons. If we look at this second example, we can see that a Gilman reagent can successfully alkylate a vinyl halide. In this case, the halogen is attached to an sp2 carbon. This tells us that the Gilman coupling is not occurring via an SN2 mechanism. The actual mechanism of this kind of coupling reaction is beyond the scope of this course. The ability of Gilman reagents to successfully alkylate sp2 functionalized carbons distinguishes them from organolithium and Grignard reagents. Another important difference is that Gilman reagents are more stable and thus less reactive than organolithium and Grignard reagents. This makes Gilman reagents more selective and thus more tolerant of other functional groups that may be present in the reaction.